Hi everyone, my name is Alex Han. I'm here to start off the webinar today. This is our first one for 2021. We are here to talk about power connector protection in rack scale architectures, and I'll be introducing Brian Costello in a couple moments here. A couple of housekeeping items before we begin. During today's webinar, all attendees are going to be muted. This is to ensure that there is no background noise. We welcome your questions and your feedback at any time during the webinar. Feel free to submit questions through the Q&A box on your screen. We will leave about 10 minutes at the end of this webinar to address any questions. If we're unable to address your question, we can reply to you directly after the webinar. For the best webinar experience, we do recommend using Chrome or Firefox. And finally, within the next day, you're going to receive an email with a link to replay today's conversation. For those of you who are new to TE Connectivity, we are a global industrial technology leader in sensor and connector technology. And technology more now than ever before enables humanity to connect. We're committed to unleashing the potential of every connection. Our 8,000 engineers serve customers in more than 150 countries. In fact, we manufacture more than 192 billion products every year, and enables high-tech applications that are advancing the future of technology, making our homes and factories smarter, enabling global communication networks, and revolutionizing medical technology, all helping to create a safer, sustainable, productive, and connected future. So welcome again. I'm going to introduce today's speaker. His name is Brian Costello. He's a system architect here at TE Connectivity. Brian is a principal engineer for TE Connectivity's Data and Devices business unit. He's part of the system architecture team, and he works directly with engineers at TE customers to better understand technical challenges they're currently facing and will face in the future. This includes aligning industry technical trends with TE Connectivity product roadmaps so that TE can deliver the right products when needed. Brian earned a Bachelor of Science degree in Mechanical Engineering from Penn State, and he started his engineering career at AMP in Harrisburg, Pennsylvania as a development engineer in 1991. Brian has over 29 years of experience in the electrical connector industry, and he holds 77 US patents. He's a certified black belt in lean design for Six Sigma, and has also instructed lean design voice of customer courses within TE Connectivity. So without further ado, I'm going to introduce Brian. Brian, are you there?
Yeah, so thanks for that great introduction, Alex. So today we're going to, as Alex mentioned already, we're going to talk about power connector protection in rack scale architectures. Go on to the next slide. So first question is, what damages connectors? Well, as it turns out, there's a lot of things that can damage connectors. From mating, unmating the connector more than its specified tested amount. Temperature excursions can cause some problems with both the housings and the contacts. Corrosive and wet environments can expose or cause corrosion in the interface, which will be detrimental. Excessive shock and vibration, again, beyond what we test to. And then of course, dust and dirt will cause real problems if they get into the connector interface. Extreme shock and thermally, that is, can cause problems especially with housings that can become cracked and fail that way. And then what we're really talking about today is hot swapping, which is we'll just get into that right now.
So real quick before we continue here, we're going to send out a quick poll, and this should show up on your team shortly here or on your screen. If you go ahead and just mark your largest portion of your damage to connectors in the field, that would be great. We'll come back and talk about those things. We're going to give it just another 15, 20 seconds here. All right. There you go, Brian.
Okay, going to the next slide. So we're seeing the mechanical shock and vibration was about half of what we see is causing damage.
Yeah.
But swapping is up there as number 2. So what is hot swapping? And so a general term, we generally referring to 2 different events. One being hot mating, which is where we are closing the path of electrical current. And in a case, and what we're really referring to is when there's a high enough voltage or current that would actually cause damage. The other is hot unmating, the opposite, where you have current running through the interface, and then by unmating it, you're breaking that path. And again, in the similar, that there's a high enough current and or voltage, where we would see damage. Next slide. So there are multiple levels of hot mate, hot swapping. I'll step through these real quick. The class 0 would be, nothing is powered on. So let's say you're plugging in a hairdryer unpowered, so it just goes in before you turn anything on, and that's the safest way that you can mate it. There's obviously no chance for any kind of electrical damage in that case. And class 1 is one step up from that, but it's a safe voltage and a very low amperage, below 100 milliamp, that's not going to cause any damage. So if you think of a lot of signal type of interconnects, would be a class 1 hot mate. And so again, no real possibility for damage because the current level is so low. Class 2 is where we get into where there's some danger here. So where we have enough current there, but there is protection to make sure that there's a limit of inrush so that it cannot fully mate with current, and current's not going to flow right away. And this is what we typically see in power subsystems, where as things are mated, there's only enough current flow there to trigger any kind of circuitry, the control circuitry. And class 3 is where there is high energy capability and nothing to protect it. So you can think of this as you have a running hairdryer and you unplug it, you're going to see a spark. This is where there can be damage depending on the way that the system is designed. And so class 3 is one thing that we really want to stay away from. Next slide. So what happens in that case where we do have a hot mate event where there is a potential, a high enough potential for voltage and current? There's a plasma will form, and that's mostly where a lot of the damage is going to come from. So if we step through a break event, where you're plugged in, you're running your device, and what you have is a low resistance interface there. And as you start to unmate the connector, you're going to have a wiping action, which is going to maintain that low resistance up until the point where you start to unmate. And at that point, you're going to have a decreasing normal force at that mated interface, and you're going to have an increase in the contact resistance. And at that point, at a micro scale, you're going to have molten metal actually being drawn between the two separating interfaces, and then that bridge is actually going to vaporize, and that molten metal, which is typically the plating, is going to ionize and kind of get dispersed, which is going to damage the rest of the plating in that zone. If there is sufficient voltage and current, a conducting plasma arc will actually form across that gap, and we'll actually stay there as long as the gap, there's enough voltage, and it's very dependent on the voltage and that gap itself, but it will basically act as a welder at that point, and it will damage and deteriorate the interface as long as it's left there. The faster that occurs, the quicker that dissipates. And so as we see in devices that have to hot unmate, like let's say a circuit breaker, and it has to be repeatable, there's a spring loaded system inside those type of devices that unmate them very quickly. and so that we don't have the damage over time. Next slide. So the type of load can actually cause more of a challenge than would otherwise be there. In the case of an unmate, an inductive load can actually cause a voltage spike. And the plot is showing a relay that's energized only to 24 volts when it's disconnected. And we'll see a voltage spike down to negative 260 volt due to that inductance. And so when the actual unmate is occurring, the voltage is not 24 volts, it's actually down at the 260 volts. So yeah, and as we know that the higher the voltage, the longer an arc can occur and the longer it will be in play, the more damage. Next slide. The other type of load that can affect the amount of damage or the capability for a problem is a capacitive load, and that's really on the mating side. And what actually spikes here is the actual current to charge that capacitive load. And so the plot here is showing a 25 milliamp circuit with a 10 microfarad capacitor in line. And we're seeing, even though it's a 25 milliamps, it's a really small amount of current, it spikes actually to 7 amps over a relatively short duration, about 180 microseconds. And so again, capacitive loads, on the mating side and inductive loads on the unmating side, are going to require a little more consideration than maybe just a purely, say, resistive type load. Next slide. So let's look at some damage. And so in this case, we're really looking at two different things. One of which is really the amount of time it takes across when you're doing that mating condition or a hot mate condition. So we're showing vary from at a relatively faster 6 inches per second. There's obviously visual damage there, but not too bad. As we move to 3 and to 1 inch per second, we can see that one of the contacts is almost completely deteriorated. And then when we get down to only a 1/4 inch per second, it's pretty much obliterated. And as we know, as that arc formation goes, it was just melting everything in sight. So we can see that even if it's the same 42 volts and 60 amp current, that velocity plays a large role in how much damage will actually occur, as we talked about with the circuit breaker kind of example. Next slide. Now, one of the things that we're working today, where we have many products out, is in bus bar connectors, and they have become more and more in use in rack scale type of applications. So in this case, we're looking at one of our bus bar connectors rated for 48 volt. And this one particular is rated for 75 amps. And we're seeing we have two different speeds that they were unmated on, and we were really looking at the unmate in this particular test. And again, we had 75 amps current at 48 volt. Only just with one cycle on that at 25 millimeter per second, we're seeing damage, on one of the tines. Now, all these contacts are common together because they're parallel to carry that 75 amp. But even at cycle number 2, we're seeing significant damage to that same contact. And as we get to cycle 10, now we're significantly damaging 2 and moderately damaging the others. And after that 10 cycles, when we look at the bus bar, it looks trashed. I mean, it's pretty ground up. When we decrease the speed down to just 10 millimeter per second, even on the first cycle, we blew away 2 contacts completely, and they just got further. We didn't even take it to 10 cycles because it was already, halfway, completely destroyed. And then we can see on the far right what the damage that actually occurs. We can see those 2 contacts kind of lined up one part of the bus bar. The conductor itself is burned back to base metal, and the insulator is melted. And we can also show kind of a video, hopefully it'll come through, of that actual mating, at that last mating at that level. So you can hear the sound of what ends up happening, and you can see that lightning strike going on again, and that's the damage from it we're seeing there. You can go to the next slide. So how can we protect against that? So the first and foremost is hot mate protection circuitry, and that comes in several different flavors. You know, the older way is discrete components. We have capacitors, diodes, and FETs, and also transistors and resistors. So individual components, but more recently, integrated circuit-based designs are really preferred, with a lot more functionality and flexibility. Yes, and there's multiple vendors that all sell hot swap type circuitry, Maximum, Analog, and TI. And what they do in effect is limit the inrush current so that it doesn't have enough power really or energy there to do damage. And then it delays the power on. Once it has that initial trickle of current to fire up the circuitry, then it delays for a period of time, and that allows enough time for everything to be fully mated. And then when full power up occurs, then everything's been mated already, so we have no chance for damage. Depending on the design, it's preferable that you do a gradual power up, and that's actually better for the overall power system bus, that you're not just turning power on. You would bring it up slowly, but that's not always possible depending on if you're really in a high power design with, say, contactors. That's what's really triggering the power on. Then you would be limited in being able to do that. Next slide.
Yep, so at this time, we're going to run another poll here. What kind of hot mate protection circuitry do you use? And we'll start it now. Okay, give you a couple more moments here to vote. All right, let me close this here and share the results. All right, so 50-50 between not using any and IC based, Brian. So back to you.
Okay, next slide. So there are some possible failure modes with using just a purely hot swap circuitry. And so two of them are shown here, the first being partial mate. And that would be a condition where you're engaging the device. So if you're pushing a power supply, but you don't engage it all the way, you only engage it to the point, in some connector designs, where you have kind of a lead-in zone on the contact. Maybe the operator thinks it's mated because they felt resistance and they didn't, give it any more, energy or push, that you have a partial mate kind of a condition. And at that point, the hot swap circuitry would, start its timer effectively, because it has, it knows that, okay, I'm seeing voltage on the line, and so I can start my countdown. The timer circuit goes through, it turns on full power, but we have that condition where it's really a high resistance interface, and so we're going to see damage in that case. So in that case, our hot swap circuitry really wasn't able to protect against that. So you have to either take that risk or have other conditions in place to make sure that that's not a problem. The other is hot unmate, and in this case, power is already running through your system, and so the typical situation would be that the system would be powered down through other means. So either through a software power off, for instance, in a data center, if a server needs to be serviced, it would typically be powered down that way. Some server designs actually have manual power switches, so if the operator gets there and it's not powered down, that they can manually turn it off. Others do not, and so for very low cost server applications, sometimes a manual override switch isn't even included. And so in that case, if the system is in, say, a fault state where an order was given to turn it down or power it off and it did not, you really don't have much recourse then. Another application, or when it can happen for hot unmade, is the operator goes out to the and maybe goes to the pulls the wrong switch or the wrong server in that case. So in that case, you are pulling hot, and the system has no way to know that's going on, and there's going to be a problem doing with that, and there's going to be damage. Next slide. So there are a couple of ways around that, and how we can maybe put some things in place to help protect. The first of which has been done for a while, which is really making the connector itself hot mateable through a sacrificial zone or contact specifically. In this case, we're showing an example of one of our connectors that has extended tip, and that's really our sacrificial contact. So if there is a hot mate or hot unmate, that's the part that's you're gonna have the damage. So we're limiting the damage zone to just where we want it to be, and not where the current of the connector is actually flowing. Because as you can imagine, as carbon builds up and plating gets worn and we have oxide buildup, that's not going to be a good place to carry any kind of current. And so the sacrificial tip or sacrificial zone provides for that. In certain applications, like on a bus bar, that's a little bit of a challenge, because if we start to damage the bus bar tip and we start to drag our contact over that, we can start to drag that debris into the mating interface, and we are going to reduce the capacity of the connector, the number of, say, cycles, or even the current capacity, because we will have a higher resistance. And then secondarily, with a sacrificial, as we saw with our test on our bus bar connector, that's not a foolproof design. If we do have a high current load and a high voltage, we could actually burn through that sacrificial zone as well. So there are limitations to how much you can really do with a sacrificial contact. And then we have mate last, break first contacts, in the connector. And the function here is that they're used in conjunction with hot swap circuitry. And so, on mating, a sense contact is the last thing, and on unmating, it's the first thing that will disengage. Next slide. So in the case of these sense contacts, they're mated, obviously at a sequence or a stitched or a sequence level. In this particular design, where we have a 1 millimeter gap between the actual contact that's carrying the power and its associated sense contact, and this is then connected to the hot swap circuitry. And so, on a mating condition, the last thing that ends up coming in contact is that, and that tells the hot swap circuitry to engage. And then in that case, we don't actually need a timer. We can immediately turn on power, because we know that the power contact has to be made because it happened before the sense contact. And on a hot swap, on a power off, or a power unmate condition, we can power off the equipment, because the first thing that's going to happen is the system's going to know, we're starting to unmate. My sense contact, just went open. And so in this case, there is the timing it's going to take to power down has to be taken into account. So if you have, let's say, a relatively fast unmating rate, or even up to 1 meter per second, with a 1 millimeter gap there, we have a millisecond of time for the sense contact the system to power off. And with most sense hardware today, that's an order of magnitude more than what it really takes for everything to actually occur. And so that's more than enough. Next slide. So for our OCP version 3 Open Rack, TE is heavily involved in that development. With our design for our IT gear connector, we've designed in a sense contact. In this case, it's showing on the power side, so it's going to sense the 48 volt. And then we also have the capability in our design then to also put it on the ground side if it was desired to really be sensing that ground return is going to 0 as your sense. Different applications can have different preferences. And we can also have both contacts in the connector if it's so desired. And in that case, it would be kind of a belt and suspenders approach where you're sensing both whether power is fully engaged and the ground as well, or disengaged on the opposite side. And you can see on the right side, that 1 millimeter, and again, it's just that the contact, is physically sequenced back, that distance. Next slide. So in summary, hot swap events, as we saw, from the examples, can seriously damage, both connectors, if it's just a connector to connector, or, if it's mating to a bus bar. The existing designs, are really geared around just hot mating, based on just sensing the power on the power contact itself. But fault events, in the IT equipment, or kind of errors, on the operator side, can expose the interconnect, to serious damage. Sacrificial contacts, can help, but they do actually require a little more complex contact design to have that sacrificial zone. If you're mating on a bus bar, for instance, you'd have to actually be kind of next to or take up more width of the bus bar to include, that type of contact. And we do know there is going to be damage there, and so that's always a consideration that it may degrade the number of mating cycles, or the current capacity, or both, by doing that. By adding separate sense contacts in conjunction with your hot swap circuitry, you get the best overall protection in any really condition, even in fault states. Next slide. So does anyone have any questions?
I will kick it off with a couple of questions that we've received here in the past 10 minutes. The first one being, do the tolerances of the connector and bus bar need to be taken into account when calculating the time needed to power down?
They do, and so, and that's what we end up. That's where you derived at a 1 millimeter, and that allows for the insertion tolerances, of the contacts themselves, and the manufacturing tolerances, of the contacts. So it's nominally 1 millimeter, and per our design, we can be a little shorter than that, and that's why we looked at having something that was a good order of magnitude larger. Or the time was in order of magnitude longer than what is really needed. But yeah, that's a good question. But yeah, it's definitely something that we have to take into account. Not something you need to really consider, unless your circuitry is such that you're pushing close to that limit. Like for instance, if you were going to really require like half a millisecond or somewhere that's getting upper in that zone, we might need to talk to you about that and just say, hey, and tell you this is the actual based on worst case tolerances, what you may need to consider. But good question.
Okay. A quick reminder as well, if you have additional questions, put it down in the question box and I'll read it out loud. Second one here, what factors affect hot mate damage the most?
I would say velocity would be a real big one, although that's not always controllable, in an IT gear or rack type of environment. In a singular device like a switch or a circuit breaker, the velocity can be handled. You can control that very well. But I would say velocity, if you can leave it in a condition where there's an arc in that connector, it's going to do enough damage, and so again, very fast velocity will not. The voltage is probably a second one, so the higher the voltage, the more potential is there. Then there's more ability for an arc to go across a longer distance, so there's more ability for that arc to last longer, again, kind of along with that whole time thing. But I would say the time that it's connected, so the velocity of the mate or unmate, as well as the voltage.
Awesome. Third question here. Do the sense contacts carry current in addition to the power contacts?
They only carry a trickle of current. They're not connected or not intended to be connected in line with the power. They're really intended to only be connected to the hot swap circuitry. If they were connected to the power, you would end up sharing current across it, which could be a challenge or problematic. And so they're only intended to carry, the kind of the milliamps that's required that it will power up the hot swap protection circuitry. So they're really terminated just to that circuitry, not beyond to the overall power distribution path. Good question.
Awesome. Here's another one. With respect to the ORV3 connector, how much improvement can be made with hot unplugging by using the sense pin, a mate last or break first?
So again, it's those fault conditions that we worry about. And so for ORV3, the specification is not released yet, but it is kind of in its final stages. And the spec will have specified sense contact. Again, it can either be on the power side or the return side. But that is part of the specification. So if from TE's perspective for our connector, I believe we will offer it in a version without sense contacts if there is a customer that needs that, because obviously it's a contact and it's a cable based product, so there's a cable attached. So there is a small cost there to having that extra feature functionality. And so if your application absolutely cannot have that condition, it's not something you're worried about, you could opt not to choose it, but the spec will have that as part of the specification.
Great. Finally, what about busbar corrosion? Say if it's in an unused position for a few years, later expanded?
So for just in a normal usage where we haven't had damage to the bus bar, the bus bar is intended or is specified to have a nickel underplate with a silver top plating, and the job of the nickel is to make sure we cover up any pores and expose the copper to the environment, so we don't have any kind of an oxidation going on of a copper oxide. And so I don't believe we specify a shelf life or a duration, but I believe just for OCP in general, it's I think a 3 to 5 year type of a situation. No concern, of just a traditional bus bar. Now, if you were to have hot mate events on that bus bar, then I have some concern because we don't know exactly how much damage occurred. If it was a very light type of event where maybe it took out some of the silver plating, but we still had a really good nickel underplate, we know that damage is going to occur on the leading edge. So where the current's actually flowing, it will be past that. So I'm not as concerned. Even over time where we might get some oxide buildup, it's very unlikely that oxide would end up as we wipe across the interface at full mating, that you would have a condition where there would be a degradation. But any damage to the bus bar from anything like that, like a hot swap event, is of concern. And again, that's why with having sense contacts and hot swap circuitry to prevent against those kinds of events, is pretty important for long-term reliability.
Awesome, thanks. It looks like that was it. So thank you again, everyone, for participating today in this power protection webinar. And thanks again, Brian, for sharing your thoughts.
Yeah,
okay.
Thanks, Alex.
Thanks again. Have a good rest of the day.